So cold starts. Generally, user expectations are if a web page doesn't load in a certain amount of time, they'll churn. So if you're looking at a strategy of how to allocate, you should be looking at trying to avoid cold starts. Sometimes they can be long depending on what your application might need to start up. But it could also be worth looking at how to find or strategize ways around how to reduce your cold start time.
Today is day 2 of the course, so we'll do a really quick recap of some logistics for people who weren't here yesterday, and then I will turn it over to Mark to talk about infrastructure. So super quickly, if you haven't seen the Voice AI and Voice Agents primer and you're interested enough in this stuff to be in this session, I think it's worth a quick skim. A lot of the things that we don't go deep into in these overview sessions have more content about them in the primer. John George posted a great audio version of the primer in the Discord channel, so you can also listen to it now. Thank you, John. Yesterday, we talked about models and APIs and orchestration. Today, Mark is going to talk about infrastructure. I've worked with Mark for many years across 2 different companies, and I learn something every time Mark gives a talk like this. So I'm really excited. And without further ado, I will turn it over to Mark.
Hello, everyone. I'm Mark. I lead product at Daily. Today's session, like Quinn said, we'll talk about hosting and infrastructure for the first maybe 2/3, and then I'll spend maybe the last 10 minutes talking about telephony. So let's get into it. So the first, I was thinking about writing this, and I'm not sure what backgrounds are from much of the audience here, but I know that I would imagine many have come from a background where you've built some type of traditional like web-based application where the stack is going to look a little bit more like REST APIs on the back end or more kind of high volume ephemeral types of requests. So just to maybe start at a base level and look at a comparison between just some of the properties of working with the traditional like web app versus real-time voice. They're really starkly different. And I know a lot coming to voice AI hadn't worked in streaming media or real-time communications at all. So this is hopefully just will ramp up into some of these use cases. So just right out of the gate, thinking about, and maybe the best way to think of it is like a REST API. So generally when you're building infrastructure or you have backend for a REST API, these are going to be like extremely short-lived requests that are stateless. They're going to be extremely high volume depending on the scale of your application and low duration. So it's more about throughput. How can we clear the queue of all of the requests coming in? What you generally see is the usage is somewhat predictable. It's going to follow oftentimes the pattern of usage of your application, but probably pretty uniformly. But it's a little bit different now when you move into the communication side of things. These are now long-lived sessions. So you have not just a hit to an endpoint and back, so it's not just a Lambda. You're going to have an actual kind of long-lived persistent session where you're going to be opening, say, a number of WebSockets or WebRTC type of connection where it's going to be persistent. You'll have some form of media streaming, likely bidirectional, if you're going to be doing voice to and from your application. These are definitely stateful sessions that are persisted through the duration of things. Volume is variable. It's probably going to match usage patterns of your application. But as far as a REST API call goes, to perform a given function, you may have 1 through n number of requests to your REST backend endpoints. Whereas with voice, you're probably going to be opening WebSockets and or establishing WebRTC connections to stream media. So they're going to be longer lived connections with like longer duration, more kind of stable network-based communication. And then resource consumption is going to be variable. It depends on what your application is doing. If you're streaming video, you could have an app, for example, that's maybe it's a voice agent that at some point receives video from a user. Maybe it starts out, becomes like multimodal. So you may have variable resource consumption even within a given application. These are fundamentally different challenges that face you on the kind of the back end or infrastructure side of things. Let's see, we'll see how this kind of applies as we move through things. One additional thing to keep in mind, we saw this slide yesterday, but just want to put it top of mind because a lot of the decisions you make will affect the latency. So if the goal is to get ultimately to sub 1 second, sub 800 milliseconds, or really kind of the ideal best case might be around 500 milliseconds if you're hosting everything locally, you have to keep in mind how your infrastructure choices are going to affect your overall latency budget. And we'll talk a little bit about this when it comes to kind of edge routing and things along those lines. But just as a reminder, we don't have to look at these things specifically. Within this allocation, network stacks and transit is some small amount of time, packet handling, et cetera. But this is really going to generally not count much of your network latency necessarily in. So it's something to think about layering on top. So now we'll start to zoom in on some of these things and we'll look at, again, the network routing and infrastructure choices. But first, just to think about this, how effectively your application might look when you deploy it. And this is going to be largely based on things that we've done with Pipecat, but there's nothing here that's magic. I think a lot of this can generally apply. But there's a notion, and I think this comes from, again, back to the traditional web world where you might think about have a machine, it can run n number of pods, and each pod is allocated a certain amount of CPU. And I almost always, without fail, get the question of how many instances can like an individual bot process handle. When we see developers trying to point like multiples of those instances to a given process. A better way to think about it, we'll look at this diagram here, but would be a given single bot is served by a single bot process. So if you look at this chart, the user might make a request to say like a server, like some backend service to initiate a request. That through some means, we'll look at this actually in more detail with telephony later, will spawn a bot process. So this might be, say, like a fast API service server running that when it gets hit, maybe if you're using, say, like WebRTC transport, you might start a room, you might pass that information to your bot, so the bot joins that room. Your fast API server or whatever type of server you're running can return that information back to the user. And then through that, they can join and meet in that room, whether it be through a WebSocket connection or through WebRTC based like session. So these are things that underpinning this, your bot runner is going to start for each individual end user request. You would start a new bot process. You would end up with a stack of these bot processes. And the goal here is to ensure that the resource allocation to a bot is consistent and is being well met. And we'll look at that again, what that looks like on a per bot basis, but it allows you to ensure that each bot process is given the necessary amount of resources to run in an efficient manner. Because again, this isn't like a stateless REST call. This is going to be some persistent connection that requires resources to process audio, to send audio, maybe upscale, maybe run some type of local model like a VAD. So this all requires a fixed amount of CPU. So this is a general pattern that we would recommend in our experience building out, and especially with Pipecat, if you've had a chance to look at some of the examples, which I think Quinn will link out to in some of the materials. This obviously isn't a Pipecat course, but we can use that to illustrate or educate on how certain patterns work. So now I think it makes sense to zoom in. Another question I get, I probably answer this once a day if you're talking to me or with all the Discord traffic that I get. Generally, and this makes a lot of sense, if you're coming from the web world, a lot of communication or signaling is done over WebSockets. And that is still highly relevant. There is a lot of signaling done, even to enable WebRTC that's done over WebSockets. But when it comes to the actual transport, so when we're moving back, the transport being specifically what's sending your media. So if it's a voice bot, it's going to be your audio streams. If it's a multimodal bot, it might be voice, video, images. It might use the data channel to send messages to and from a client. So it's going to be things that are in that world. If you read some of our material, you might think WebSockets are just evil and we shouldn't use them at all. And you might think, geez, Daily is a WebRTC company. Are they motivated in some way to say this? I'm just going to come out and say that WebSockets absolutely have a fit. We'll talk about this in the telephony world. I'd say the thing to highlight is WebSockets are really well suited for server-to-server applications. Generally, the issue with WebSockets are they're going to be a TCP-based protocol, and that's going to have more challenges with any type of retransmission, packet transmission. So if you get any congestion and or packet loss, you're going to see things like head of line blocking, where that can introduce latency or jitter into the connection. And again, that retransmission just says TCP is not really built for that. Whereas something like a WebRTC, and there are other protocols emerging that are well suited also for real-time media, but with UDP, you're going to get just much better throughput with all sorts of magic that happens that, I don't know, Varun is an expert. So if you ever want to know like anything about anything with WebRTC, you can reach out to Varun, but there's a lot of benefits from using UDP. So with WebSockets, though, not well suited because of the TCP connection for client server, it may be totally fine to run if you want a quick hack to get up and running on your local machine just to get going. And a lot of our Pipecat examples do use this. But the main application would be server to server, primarily being that, say, you have your application running in some server in a data center and you're reaching out to a phone provider that's also running in a data center somewhere. They're going to both be Ethernet connected with stable backbone connections and really should have pretty ideal network conditions. So you're unlikely to see that type of high or really much, if any, packet loss or jitter. You're going to see these ideal connections. So the server to server applications are really well suited for WebSockets, which telephony is the big case. We'll talk a ton about that here at the end. Now, as for WebRTC, WebRTC also has a fit, and it's not that WebSockets are the only thing for telephony. WebRTC is actually a fantastic medium for that, as it is really largely built for peer-to-peer, real-time communication of media streams, among other things. So you get a lot of optimization done for the media. For example, if you're running on a browser, so you're building a client-server application, you're going to get really nice audio quality. You're going to use Opus codecs with a very reasonable bitrate throughput if it's just audio. And it's going to have all sorts of niceties built in, like media controls. You can access things like get user media in your browser to give you access to controls. And you have built-in controls over things like echo cancellation. So again, if you're building or thinking about building with WebSockets on a client side, you're going to sorely miss things. Actually, just responded to someone yesterday about this, but where there's complaints about, gosh, my WebSocket server running client to server doesn't have any type of echo cancellation. When bot speaks, it hears itself and interrupts itself, which is just something you just simply won't get with WebRTC. So there's just a lot of benefits here. Also, just it's incredibly resilient with forward error correction built into a lot of the base algorithms. So you're going to get a lot of resiliency with suboptimal packet loss or jitter or latency values up to a pretty reasonable point. WebRTC is extremely flexible. I'm speaking about this generically. We'll dive in, we'll really zoom into this in the telephony section. But just if you were to think of anything, the general takeaway is WebRTC is a great fit, period, for media transfer. And if you're thinking about WebSockets, it is a good fit for telephony or server-to-server use cases. All right. So now zooming in a little bit more into latency, I borrowed this image and I'm going to talk pretty much directly out of the voice guide that Quinn wrote here. But this is something that we see having built out daily as a WebRTC company as well, is just generally your network routing. So things to consider are one, deciding or going with a transport provider that has as many global points of presence as possible. The goal being here that if you have long haul communication over the public internet, you're going to see higher latencies, generally on the order of, I don't know, tens of milliseconds, but it can be worse, especially with variable network conditions. It depends where you're routing from country to country. The big takeaway here is that the ideal thing, and this is something that we learned and really the whole WebRTC community learned, is that if you can communicate with your local edge connection, so if you have a local server, if you're running, say, I think in the case in the book it was London, if you're connecting out to Frankfurt or US2, you're going to have a very short hop. So pretty much anywhere in the world with kind of modern communications providers, you can look at that first hop latency to your server on the order of 15 to 20 some odd milliseconds, somewhere in that range with some fluctuation based on location. But between that short hop, then the majority of your communication, so if it's communicating out to somewhere, let's say your bot is running in like US West 2, you're going to have over the public internet, you might see something like 140 milliseconds over public, but over the backbone, so let's say it's AWS to AWS over their backbone connection, you may save upwards of 30 to 40 milliseconds. So that might not seem like a lot, but again, we're playing this game where every little bit matters. So how do we chip away at all these different components? The biggest contributors being likely the ones that influence you, you'll see are your service providers, the transcription provider, your LLM, your TTS, but the network layer certainly does matter. So anywhere you can save, and it's not only just latency savings, you're going to have more stable communication over the backbone. So these are things to consider when you select your transport provider. It will definitely have downstream consequences to your bot. All right, so now we'll start to move into thinking about the actual hosting and infrastructure that you need to consider when building the bot. A rule of thumb, and this isn't for all, but let's start just with voice AI. We've done this. So we launched last year a platform called Daily Bots, which we've since wound down. But we learned a lot there in playing around with what the allocation was for just a standard voice bot. Now, if you're going to run in Pipecat, this would be some type of local VAD that's running to do near instantaneous speech detection. It would be running all your Python processes, not counting running in any type of model locally. This would be assuming that all of your services are going to run off machine, because that's just a different consideration altogether. But a standard voice bot, the general rule of thumb is going to be around a 1 to 2 ratio between CPU, where you have, say, half of each CPU per bot instance. So when you're thinking about your allocation, your pod that you may launch should receive or have access to around half of vCPU. And then for memory is going to be about, so for a vCPU to gigabytes, it's going to be 1 to 1 gig. And that assumes, if you think about what a voice bot requires, it's going to be, again, running some type of local VAD likely. And the processes, it's going to write things to memory, but not a lot. So it doesn't need a ton. I didn't mention it here, but storage is something that effectively like isn't a main consideration. So those are going to be the main things. And then with network throughput, your egress from your service provider is probably going to be pretty low. This is a ballpark number, but if you're doing like WebRTC audio over the web, your browser targets somewhere in the range of like 30 to 40 kilobits per second, depending on the bit rate you choose for audio. I don't think you'd see anything higher than 60 kilobits per second, but that's going to vary based on some circumstances. So resource-wise, it's a fairly light footprint, and I don't have it here, but Quinn has this fantastic calculator. I have answered many questions about how do I CPU optimize my bot and how do I account for my infrastructure. When it comes to cost, this kind of blew me away. I just saw this 2 days ago. Quinn had pointed out, given all of your bill of materials where you have your STT, your LMTTS, any other services you may be using, your cost is really and likely going to be somewhere on the order of like less than 1% of your overall cost. This is if you're building your own infrastructure, you've decided to do the work yourself. The actual cost, like operational cost, is going to be extremely low. Now, this doesn't account for the manpower put in, which of course there are platforms that have popped up like Vapi layer code or like a Pipecat cloud to try to save or offload some of that non-recurring engineering cost. But the actual kind of runtime costs for the hardware itself is going to be pretty low. The point being, like, to try to optimize on CPU, even if you allocated one vCPU per bot, is something that isn't going to really matter in the grand scheme of the overall operational cost of running your bot. Now, if you're running video, you'll absolutely require a little bit more CPU. Even with some low frame rate video at the half of vCPU, you're going to see around times where things are starting up or you have some processing happening, you might see some frame rate loss in the video, which is going to be directly corresponding to the lower CPU if you try to run on half of a vCPU. So you do need to think about different profiles based on it. But this is a good starting point if you're building for voice AI and looking to deploy on your own. It's definitely a good start. So I guess, yeah, where to get started. I know that many voice AI is still extremely new, so many are just getting started like at all. You may have just found Pipecat in the last few weeks, maybe looking at deploying. A general bit of guidance would be just simply out of the gate, just get it working reliably. There are a lot of considerations here where we'll talk a little bit about cold starts. That's the biggest enemy when it comes to balancing resources. But the goal being, start with something basic, like a simple container solution. Maybe you're running like Docker or building Docker containers with some really light tooling around it. So you're just deploying a Docker container into maybe your own VPC or on your own VM. It'd be a really cost-effective way to just get started. You could over provision, you could just run a certain number of instances based on whatever traffic projection you have. And again, your costs are going to be relatively low in the grand scheme of things. But as you're getting started, this would save you operational cost. Doing all of that hard upfront engineering, we've learned this the really hard way building out Pipecat Cloud. It is a months upon months long endeavor for people that do infrastructure for a living. It is just a hard, long slog. But if you want to just get something up and running, you're building a demo and you want to, maybe you're going out to try to raise or demonstrate something that you're doing to the community. Maybe over provisioning to some extent is a fine, simple strategy. Once you go to market, if you think about the second phase, there are other things to consider. You may look at pools of resources or running some amount of idle capacity. And this would assume you have some idea of what the usage patterns are around your application. This is easier for you if you're thinking about just your app. Maybe you're a Monday to Friday, 9 to 5 type app, or maybe it's a B2C type application where it has 24/7, 7 days a week traffic, but it fluctuates organically based on like geographies or times of day. Once you get a sense of how that looks, you can start to look at scheduling and spinning up warm instances or spinning down warm instances and running some amount of idle capacity. You'll undoubtedly have surges in traffic that you can't predict. We'll talk a little bit about that actually in a second. So it can make sense for just as like a starting point to run some amount of idle capacity. We're doing this exact thing with Pipecat Cloud, where for every active instance, we'll allocate some percentage of another instance that's running. That way, as you have traffic growing, you can ensure that you're going to avoid the next cold start. For your own deployment, it's something you can look at scheduling that and picking out your own strategy, but this is just traffic modeling for your own application. Moving into kind of the last category, which is going to get more complex, all of this looks fairly similar to running services as far as auto scaling goes. So scaling up based on demand or usage, you'll look at having an autoscaler that might try to balance loads. And this is again where that idle capacity might come in, whereas you scale up, you might have an algorithmic scaling where you may spin up a bunch of instances for your first few to avoid like a quick spike in traffic hitting cold starts. Because again, cold starts being the enemy here, especially with voice AI. If you click a button, you expect someone, an agent to talk to you, and it takes longer than your user might likely churn. You can think heuristically of how to look at this, where maybe you scale up a bunch of instances, and as traffic goes, you just ensure you maintain some type of buffer. But your auto scaling algorithms can handle that on something that, as you figure out scheduling or your usage patterns, are going to be probably the biggest way to be proactive about planning things out. So cold starts, I'm just calling it time to first word. So I was reflecting on this in working on this presentation, but generally user expectations are at this point, we've been 30 some odd years of people really having strongly acclimated to like how the web works. For example, if a web page doesn't load in a certain amount of time, they'll churn. So there is that behavior it carries over into the voice world, into real time. That appetite for waiting might be on the order of 2 to 3 seconds. It's very low. On the phone, there's the rings. There's like a sense of filling the void when you're waiting. There's also an expectation, human to human, that calls aren't answered instantaneously. So there might be a little bit more wiggle room there, but still, the expectation, if you look at this, let's say no more than 5 seconds waiting. So if you're looking at a strategy, so back to this slide of how to allocate, you should be looking at trying to avoid cold starts. Sometimes they can be long depending on what your application might need to start up. But it could also be worth looking at how to find or strategize ways around how to reduce your cold start time. So if you're containerizing your application, for example, you might want to bake into your AMI as many of the possible things that you have. Like maybe if it's Pipecat, maybe it's the base code, your OS is going to be built into the AMI. Maybe some of your dependencies get loaded in, which is easier if you're running your own app because you control your own dependencies. But that may be a way to reduce the time of, say, downloading the Docker image and then spinning up all the resources. So it may help to curtail some of the cold start timing. Your primary mechanisms here are going to be running warm capacity. This is not dissimilar from running web applications, but having some amount of warm instances there so that if someone hits your start endpoint or hits a button to call an agent, which results in the start endpoint getting called, there's going to be an agent that comes online within 2 to 3 seconds. Again, otherwise, if you're waiting 20 some odd seconds, so you're going to see churn when that happens. And scheduling is going to be the biggest thing here. So again, understanding your usage pattern. If you know that, say, 9 a.m., you get a lot of inbound calls. Maybe you're like a pharmaceutical, like local pharmacy, let's say. You get a lot of inbound calls when your office opens or a doctor's office or something. You are going to want to, in advance of that, understanding your historical usage in, say, 1 to 5 minutes in advance, because people may call earlier. It would be a way to ensure that you have capacity there. Because you might see that spike in traffic going from really low or maybe near zero to something more Now, I know that our example is a little bit artificial because in voice AI world, I don't need to call based on calendar time, but maybe you need to get transferred to a human. So just forget about the example. But the key here being that if around a given time event, you should understand or do your best to characterize or understand the historical performance of your app with regards to usage so that you can look at scheduling and spin up those warm instances in advance. So, effectively the takeaways being ensure you have available capacity, understand what your usage patterns look like, and do whatever you possibly can to ensure that if you hit a cold start, you can keep that time to something reasonable. Like in the very best case, it can be under the 5 second time period, but if it needs to be longer, that's something that you can handle. And I've covered most of this here. There's predictive or reactive ways to approach things with regards to scaling. And reflecting on this, really, I do think predictive is probably the way to go for real-time media because it's something that, again, it's hard to spin up resources. So it's something that you may want to really understand your historical patterns. I would say, though, it makes sense to have fallbacks more in the reactive world. This might be something that you think about actually in your application development, where in the event that, let's say, you get a long join time, maybe you have some type of UX in your application or through your phone to ensure that gap is filled. Because the worst thing would be it takes 10, 15 seconds for someone to get to their experience and they churn by the time you get there. So to be predictive or planned in advance is going to absolutely be your best, but you certainly need to think about application wise how to handle that. So on the infrastructure side, just to maybe give you a little bit of the lay of the land, there's a full spectrum of things from all the way from on the left side, the hyperscalers. These are going to be your AWS, GCP, etc. You're building with primitives. These are all the base level machines that you're going to get and deploy, run your own scheduling and auto scaling and do everything yourself. And ultimately, if you're building a platform that is going to run at scale, you probably want to build on this. But to get started, it can be prohibitive in terms of both skill set to get there and time, especially if you're on venture funding, you might be on a really short clock and need to get to market as fast as possible. We see a lot of popularity out of the container platforms, like Fly is one that's really popular, mainly because of the cost structure, but they are going to enable you to build and deploy your Docker container in a relatively simple way. And a lot of these platforms, specifically Fly, are really well suited for this because they support both TCP and UDP traffic. So you could run both a client server app or a SIP enabled telephone app on Fly without an issue. Whereas there are some platforms out there, like I know that Google Cloud Run is very popular, but after working with some customers, we found out there's a hard stop there that if you need, say, WebRTC or UDP, it's a TCP only platform. So if you're building phone deployments, you could run on something like GCR. But otherwise, looking at something like Fly is actually a really popular option. In the world of, it's called ML focused providers like a Cerebrium, Modal, Baseten, Firework, there's a bunch of them that do really excellent work. We have some examples from, I think, all of these in Pipecat if you're interested. But if you're running your own model, so this is either you've built your own speech or you've done some fine tuning of an LLM, you can deploy and run these inside these cloud environments. So they're going to give you GPU accelerated workloads that let you run your own workload. And if you're really looking to knock it out of the park with regards to latency, you can get latency down to extremely low values. Quinn and some of the team, I wasn't involved in this directly, but did an experiment last year, which feels like a lifetime ago, to see how fast things could get. And I think we saw sub 500 millisecond times. I don't know if I think that was running on Cerebrium, I don't recall, but it was running everything locally. It was a local version of DeepGram. I think we were running probably a Llama model, and I'm not sure what text to speech model we had at the time. But it was when you cut out those network latencies and you run and also inference is done on the same device, you can get to extremely low latencies for your bot, almost like unnaturally good. It's definitely within that 500 millisecond envelope, which was cool to see as just as a proof of concept. But these are great to check out. Again, really good examples on Pipecat if you're building on Pipecat. And then lastly, there's a different category that's emerged over the last few years. Vapi was one of the first ones there. We've worked with them for a number of years. They build on our WebRTC layer, but they have a fantastic platform that is in the kind of medium code. They're not quite like some of the providers you'd see like a retailer Bland that might be like extremely low code, but Vapi gives you a lot of flexibility and choice over your models. So they are in the world of infrastructure provider. They do a great job. I personally don't have a lot of experience with layer code, but I know that they're one of the sponsors here, and I'm sure we'll have some great things to share. So I'd encourage checking out their platform. And then lastly, we've done some work around Pipecat to make hosting, deploying, and scaling really easy. So with these platforms, generally what you get is that you have a pretty significant layer of customization over your code to some varying degree, depending on the platform. But all of them will, again, if we're going from hard to maybe moderate in the middle to really easy for deployment at the end, these are going to be more white glove, like very easy services to deploy on that you could launch like in I don't know, 10 minutes. So if you have, say, a Pipecat bot and you wanted to launch on Pipecat Cloud, you could have it up and running on the order of minutes. Again, going to be a little more costly, but it saves you a ton in terms of your operational cost and doesn't require all of that infrastructure experience. So if you're trying to get to market fast, these are great options to consider. So just a quick terminology review. I won't belabor this, but PSTN, public switch telephone network, you can think of this as like your actual phone call, but it's going to be generally your phone provider, like a Twilio or SignalWire or a Telnyx or a bunch of options out there. And then SIP is going to be your session initiation protocol. This is a fairly old standard that I think I first touched when I was working on video conferencing back in a previous life, but it is still highly relevant. And you'll generally see it when it comes to like enterprise telephony, VoIP-based systems, or call centers. This is going to be required for hookups in those cases. Generally, we'll be in the world of more complex call control. Just as a reminder of these, we're going to use both terms throughout. So if we look at a call flow at a very high level, what this looks like is the caller will make a call via a phone number, which you purchase from one of these providers. Those calls get routed over just the telephony network to your CPaaS provider. That might be a Twilio or Telnyx or someone. There will be some interface then between that CPaaS provider and the bot. That can look like a bunch of things. So there's a bunch of ways to consider this. This can be a WebSocket-based communication. It can be WebRTC. It could be SIP. We're going to look at a few of these and what they might look like. Of your connection options, you have a lot of choices, maybe from simplest to most complex. In the simplest world, in terms of the WebSockets, generally this is a mechanism that providers like Twilio had implemented to allow for exchange of media streams. It's a fairly rigid way to communicate as there just isn't a lot of control over it. You're basically setting up a direct WebSocket connection between your bot and the CPaaS provider, where Twilio is the interface with the telephone side, and they're just simply exchanging media streams. So there's no control over any type of intricate like feedback system around transferring or track controls or things on that order. It's generally going to be more of a fire and forget type of interaction when you want to make changes like forward a call, for example. But on the plus side, it is extremely simple and very fast to get started. Also, the latencies with regards to WebSockets are really tremendous in this regard. It's just a direct network connection, so there's not a lot of hops and not a lot of overhead in terms of connection. In the middle is WebRTC. So you can see this either through just a PSTN direct connection or in complement with SIP, but it's going to generally offer you all the benefits of WebRTC, like track level control, high quality audio, the ability to do more involved transferring and track handling. You're going to get encryption and error handling and things built in. So it does provide for a nice benefit. It does add a little bit of complexity to things, but there are certainly benefits. And if you're building for use cases where you may forward to someone, say that's on a web client, this becomes an absolute must-have because in the WebSocket world, you just simply can't do that. And then last is going to be SIP. And again, how you may end up in this world is if you're connecting into call centers or things, and it's going to have some level of coordination with other protocols like WebRTC. So let's look at an example. We'll look at two examples. A simple WebSocket connection. So you're going to be your caller, your CPaaS provider. You would be running some type of server, maybe for Python applications. This is a fast API server. And then you'll have a bot. So your caller makes a call. The CPaaS provider is going to receive the call. They would communicate with your server in some way, very likely emit some webhook to your webhook URL. So you would get a post to that to notify that the call has come inbound. In the Twilio case, and Telnyx has their own with the TextML, but TWIML is the XML format that Twilio uses. So you would respond from the server back to your CPaaS provider to request the WebSocket connection be initiated. It then gets initiated between the two. So you now have a pipeline between in the response to the server, you get basically initiate the WebSocket for communication between your server and CPaaS provider. That WebSocket can be used and passed into your bot to initiate effective that information flow into your bot through that WebSocket connection. So if you're using, again, in the Pipecat world, this would be like a fast API interface. There would be some way to serialize the information that's coming from Twilio down into your bot so it actually gets turned into things like frames or usable information in your application. Once that happens, your bot can then communicate. So that is a way, that is how it's going to establish that WebSocket connection. Actually, the arrow is going to go to the CPaaS provider because it's going to communicate through the CPaaS is going to be your telephony interface back to the user. So I guess this arrow should really extend to about here. And on the SIP side, this is again more powerful, a lot more control over things specific to certain use cases, but it comes with, as you can see, more complexity. Now the flow here will it'd be initiated in a similar manner. We have one additional role. In this case, you're going to have, let's say, for the sake of it, a WebRTC vendor like Daily. So your caller makes a call over the telephone network. It's received by your CPaaS provider. There would be a web hook or some type of means to communicate to your server to let it know that the call has been received inbound. Your server needs some way to communicate and to have them be interconnected through some SIP-enabled interface. So this is to ensure that you have a WebRTC connection back through. So your server would create, say, a SIP-enabled WebRTC room. It would also initiate the bot process. So it's going to do both of those in parallel and put the caller on hold. So these are things that are going to happen very sequentially. The caller, from their perspective, may just continue hearing a ring. So they would be, unbeknownst to them, this is all happening. So you can play actual ring sounds to make it sound like it's just ringing through. So once you get a signal that your room is ready, so this SIP-enabled room, in the case if it being, say, something like Daily would emit a signal to your bot that lets it handle it in its event handler to actually initiate or make the final connection to the call. The bot knows the communication is going to be via this SIP URI and would send it all the way back to your CPaaS provider and would then join your CPaaS provider and your bot would then be resident in the same room communicating via WebRTC. So that's how they would both effectively be able to communicate. So it is more roundabout, but in doing so, you have a lot more call control. So your bot has the ability to interface through the WebRTC vendors like native controls for tracks. So this would be relevant in the case of if you want to do a warm transfer, for example. To define this is the caller talks to a bot. The bot realizes it needs to be forwarded to another human. In this case, the bot can actually brief the human agent before the human agent is back in the mix. So through this more complicated flow, you have the ability to do track level control. So you can keep the initial caller, the bot, and the human agent all in the same room, not having to forward around to different numbers, but you can actually control at the track level so that the bot can speak to the agent while the human hears hold music. So it allows for this more sophisticated control, which you can build out interesting and really helpful UXs when it comes to that forwarding scenario. In terms of cold transfers, you can do that, of course, with either the WebSocket or WebRTC or SIP-based interface, but this is going to be basically in the fire and forget scenario. You're just going to forward the call onto a new number. No context sharing between the bot and the human. Someone would just know that if I get a call, I've got to then start from scratch with this person. But that is certainly a case that we see and one that you can consider with how you build out. And last, DTMF is something that if you get into this world, just think of it as like the tones that are emitted or key presses emitted whenever someone presses a menu. You would see this in the world of IVR systems navigating a call tree.
All right. Thank you, Mark. So many questions. I am struggling to keep up in the Discord, but we curated a few. Maybe we'll just go top to bottom. The first one was who's seeing 350 millisecond latency for LLMs. I think that's a totally fair question. I made that table a long time ago, and I think two things were going on in that table. One is that OpenAI was delivering actually really good latencies with GPT-4o when I made that table. And I think they've spread their latency numbers out a little more, maybe as they've grown and their models that they're hosting have grown. I don't usually see 400 millisecond from OpenAI these days, but maybe that'll change again. Also, I was using Grok a bunch when I made that table. So I was trying to split the difference. Like, what are you going to see in various tools you're using? Maybe it's fair to say 350 millisecond TTFT from a big SOTA LLM is just a bit aspirational right now, but I think we're getting closer. We're consistently seeing under 500 milliseconds from Gemini Flash, which is cool. Do we have any stats or general insights into how much the memory usage for bots written in Pipecat? And again, this is not a Pipecat course, but context for memory growth. Don't see in the typical voice to voice code that I've looked at closely memory growing. But if somebody else has a different experience, let me know. I would like to see everybody's experience with all kinds of different code patterns and bot frameworks. Somebody posted that they want to understand. Mark suggested from media to bot application server, it should be WebRTC, and in between applications, it should be WebSocket. So I'm going to translate that and then into like how I understood the question. Then we can talk more about it if I misunderstood. At a high level, what I tell people is use WebRTC for server to server connections. Server to server means somebody's big infrastructure in the cloud and your bot running on a good host with good internet peering in the cloud. WebSockets is great. Don't use WebSockets for client to server communication, meaning if you've got a web application or a native mobile application that you expect people in the real world to use for real time, very low latency audio, you should not be using WebSockets. And you will not necessarily see those problems when you are testing. You can test all you want on your good device and generally pretty good network connection that you have because you're a programmer. You will almost never see a latency issue, but 10 or 20 or 30% of your users definitely will see all kinds of problems with WebSockets in the real world. We have lots and lots of metrics on this. And those problems are not the kind of problems that are issues if you are sending relatively small amounts of structured data in relatively bursty chunks, but they will show up as audio issues for real time audio. Latency will grow. You'll get lots of audible audio issues as the various parts of the network stack try to figure out what to do with your TCP packets. And you will not know because you will not have enough monitoring, because it's essentially impossible to build enough low level audio stream monitoring into a WebRTC transport stream. There just aren't the hooks for it. Like in theory, you could probably do it. That's a whole engineering team's worth of effort. In practice, all that stuff is built into WebRTC. So you will both have much more reliable performance client server with WebRTC without doing anything. And you will have monitoring so that you can know what percentage of calls are having problems. We can talk a lot more about WebRTC versus WebSockets, but like use WebSockets for server to server, the Twilio server to your bot server, WebSockets, awesome. Don't use it. Don't use WebSockets for client server.
I
Yeah.
think you made two inadvertent. You had said out of the gate that WebRTC was great for server to server, but
Oh, I'm sorry.
I think you meant website. I'm just going to clarify WebSockets. And at
Yes.
the very end, you said it would be impossible to build that type of monitoring into WebRTC, but again, you meant WebSockets. For example, with Pipecat, when you interface for, say, STT or TTS, those are all WebSocket-based communications and are highly reliable. We don't see issues. Now, WebSockets have their own challenges because you have to build reconnection logic in, and that's a pain, but it is, as far as just a communication mechanism or like a protocol, it is a good and reliable one on the server side.
Sorry about mixing up the terms. I'm trying to talk fast when I do this because I feel like I tell this to people all the time and I don't want to sound like I'm repeating myself. But maybe the fact that we have this conversation over and over means that it is like an important thing for people to fully wrap their heads around, that for server to server with good internet connections, WebSockets is great. For client server, for native mobile apps, for web apps, WebSockets will cause you problems in production for real time audio. Can you talk about splitting runner and agent machines into separate entities? You often have a kind of web hook server, for lack of a better term, that forks a process or spawns a bot in some way. That's a very common pattern. The reason you do that is just because the workload of the bot runner is very traditional. Like you're taking a API request and then you're doing something and you're returning. So put a box around that and run it in the most standard possible way you can. Then how you run the actual voice AI processes is going to depend a lot on what stack you're choosing for voice AI and how you're architecting your voice AI agents. And there's no standard playbook for that yet. As Mark was saying, those workloads are all so specific and new and different from like HTTP workloads. You're going to have to do something custom for those. So you split the two workloads because they just look different. They behave differently. One of them is very standard. You can use all the standard tools. One of them is not standard at all yet anywhere in the internet tooling world. We can talk more about that if I missed the point of the question. What does drain time mean? So drain time is you've got these long running connections. You've got somebody on the phone or on a WebRTC connection from a client device with your bot. You need to not cut off those users when you do things like deploy a new version of your bot software. And again, this is a difference between traditional HTTP workloads and these real-time communication workloads. Typical drain times in the default Kubernetes configuration, for example, are like 15 seconds or 30 seconds, because the assumption is that if you're doing something in an HTTP request that takes longer than 15 seconds to return, there's a pretty good chance it's broken anyway, or at least this very small number of very long requests. If you ended them, it's fine. That's not true for a voice AI connection. Like most calls are much longer than 15 seconds. So you need to account for that somehow. In the server level orchestration world, drain time is, I think, the most common way to refer to how long do you wait before you terminate an existing node when you do something like update configuration or push a new version of the software that node is running. What does cold start mean? So cold start just means from the time you don't have a resource deployed to the time you can actually run a workload on that resource, how long does it take? And in the Gen AI world, we're all talking a lot more about cold starts than we used to because we have so many GPUs in the critical path of our workloads. And getting GPUs up and running with big models loaded on them is super slow compared to everything else we've been doing in the cloud for the last 20 years. But cold starts are a problem no matter what you're doing in the cloud. And as somebody said, like AWS Lambda has optimized that stuff really nicely with a bunch of great engineering and a bunch of over provisioning of capacity, which they charge you for. So a bunch of us are trying to do similar things for voice agents now as we're building out this infrastructure. But there are really only two knobs you can turn. One is make everything in that cold start sequence as fast as you can. And the other is provision more capacity than you actually need at the moment. And one of those is engineering work, and one of those is economics of your system and use case. If anybody knows any other knobs you can turn to fix the cold start problem, I would like to know about them. Maybe very short digression, just because everybody who's building this stuff is trying to figure this stuff out. And in case it's interesting to people, we made the choice with Pipecat Cloud to use Docker because our goal was you can push any Python code to us and it will run. And that's a sort of Docker shaped problem. When you go to more specialized container runtimes or architectures, you can probably get things going faster for some parts of the startup than you can with Docker, but you probably have trade-offs about generality. So that's what we were thinking. And if anybody wants to go deep on like container architectures, that would be a terrific either Discord channel or opt-in live discussion session. Let me know. I like container architecture stuff. Awesome. Thank you, everybody. See you soon.